Good evening, everyone. I'd like to thank you for joining the SAE Southern California section. We have a very exciting topic this evening with regards to additive manufacturing and two various themed hosts from Nexa3D. They'll be discussing different automotive applications, but before we get into the actual program itself, just would like to cover a few housekeeping items. With regards to SAE SoCal, you can see we have our social media advertising. So you can find us at www.saesocal.org or also on LinkedIn, Facebook. And we'd like to encourage you to subscribe to our YouTube channel, which is youtube.com/SAESocal. Also, for those interested in joining, you can see the web link as well. And that's, again, our web link, sa.org. And then myself, my name is Delbert Boone. I'm the Meetings and Tours Vice Chairman. And you'll see my email address as well, and also Dean Case, who's our membership chair. We'll also display this information at the end of the webinar. So for those who may have missed it, just stay tuned and I'll show it post Q&A. One last point, for those who have questions during the webinar, please enter those questions into the Q&A chat box, and we'll try to take those and answer them via the chat box itself or towards the end of the presentation. We'll get to the questions at the end. So without further ado, I'd like to introduce our two speakers. The first gentleman, Mr. Kuba Krasic. He's the head of Powder Bed Fusion Business Ops. He's a serial entrepreneur and experienced business development as well as project management within automotive additive manufacturing realm. The second gentleman is Mr. Brent Zollinger, who's the head of operations. He specializes in automotive as well as other applications as well. So without further ado, I'd like to introduce Kuba and Brent.
Well, it's thanks for that great introduction. I'm excited to come and we're both excited to come and talk to you today. I'm going to talk primarily about a project that we did a year ago, which highlights the benefits of additive manufacturing, particularly when coupled with generative design tools and the use of castings. Let me see if I can share my screen here. Is that working? You can see me okay?
Not yet.
All right, so the project I'm going to talk about involves a few companies. So I'm going to give you a little bit of background on these companies. It's a lightweighting project for the Arcimoto electric vehicle. And this project was a combination of work done with Nexa3D, ParaMatter, which is a generative design software tool, as well as Exponential Works, which is like an incubation hub for Nexa3D and ParaMatter when they were starting up. So this was a project to see how much weight we could take out of the vehicle, given a relatively modest budget and in just 1 month of time. So it highlights how quickly some of this technology can be implemented. So to introduce you a bit to the project, I have this little video. And what we did is we took components of this Arcimoto vehicle that Arcimoto essentially donated to the cause. We redesigned them using topology optimization on this ParaMatter software called CogniCAD. And then these components, we also then printed castable patterns on the Nexa3D high productivity printer, the NXE 400.
Excuse me, Brent. I just want to ask if everybody can see your presentation because I can see it.
You can or can't?
I can.
That's why I was asking.
Yeah.
Yeah, let me go back to Zoom. The hotkey maybe didn't work.
Yeah, no, I got the information from chat that nobody can see it. Oh yeah, now we got it. So if people
Okay, so I'm going to start over this video then. So in this project, what's amazing is how quick it is to do generative design. Some of the challenges at first are essentially creating your starting file or your build envelope and understanding the different ways for the analysis that you would need to build in your constraints and load cases. The real value that's coming is from the ability of additive manufacturing to make these organic shapes easily. And then casting is an ability to make them affordable. Printing in polymers gives you a much faster speed and a much lower cost basis than direct to metal printing alternatives out there. So printing patterns is not too out of line with conventional tooled patterns, especially when you're at lower volumes. The NXC400 printer has a cost and productivity basis that gives you the chance to go to relatively significant volumes for some of these kind of lightweighting applications. So this project was done as a feasibility study or proof of concept. You can see there the CEO of Arcimoto and the CEO of Exponential Works and Nexa3D showing off the vehicle. So this vehicle, if you're not familiar with it, it's a 3-wheeled electric vehicle that sits 2 people in tandem. It's street legal for the most part. I think there may be 1 or 2 locations where it has some restriction or requires, I should say, it requires a motorcycle license in a few states, but most places it does not. It's got a 75 mile per hour top speed, 100 miles of range in city driving, 77 horsepower, and under $18,000 starting MSRP. So an interesting vehicle. It's been interesting to watch this company as it grows. This, I think, is their 5th or 6th iteration of the vehicle. And then I'm going to introduce Nexa3D, which we're an additive manufacturing company with the target to make high productivity additive manufacturing solutions, digitizing the world's supply chain sustainably. So Nexa3D is focused, 1, on photoplastics, which is what we used in this case. The NXC400 works with photoplastics or photopolymers, and specifically here we did castable plastics, which can be used for investment cast patterns. And then on the right, you'll see the QLS line, which is sintered thermoplastic materials. And this is another high productivity area where we can get, both are offering essentially tool-less manufacturing methodologies that allow a high level of agility to the supply chain. And we're seeing a lot of interest from many different industries on seeing how either parts can be done at low volume without tooling, or how they can be done on demand for spare parts, or how they can be optimized to make non-producible geometries otherwise, due to some organic shape or difficult to tool shape. So going through the learning curve with additive, I come from kind of a conventional background in where a lot of castings were used in the turbo machinery market, supporting automotive, both passenger and commercial vehicle volumes. And that's one way where I came to be familiar with both of these So the trick here is building up a supply chain that allows, that's one of the tricks. The other trick is developing the know-how to design for this process. And often it's best to design additively rather than subtractively. And I'll try to explain that a little later. I'll go next and just cover a little bit about the printer that we used. The model printer is the NXE400. This is printing one layer of photopolymer at a time. And so it prints relatively quickly. Depending on the resin usage and some other variables, we're able to print, let's say, a full build volume in under 2 hours. That means that we can make, depending on the size of the part, relatively significant volumes. So we have some cases where we have maybe 30 parts fit on the tray and we can print thousands a day, or we have a few larger parts like some of the ones I'm showing here, and we might print 10s or 20s per day per printer. So the printer is established to kind of support production applications and high productivity, as well as a very low cost of ownership. For example, we have a number of customers, one of which is Flyer, which is an electric bike manufacturer that's kind of in the similar industry. And they're using both elastomeric type materials as well as like conventional high durability thermoplastic materials. I'm sorry, not thermoplastic, but the thermoset materials or photopolymer materials we're using in this process are not meltable, let's say. So the thermoset, so once they solidify, they stay solidified. They have a lot of variations in chemistry, and we work with the world's leading chemistry compounders like Loctite or BASF or Henkel's to develop resins and tailor them for this process. So we have some resins that are like ABS in performance, some that are like acrylic, some that are like polypropylene, some that are like elastomers or soft rubbers. And then the other company involved in the project is called ParaMatter, and they're a software company, and they make a product called CogniCAD. You can see some other projects we did similar to this with an earlier company where we did some other lightweighting on another vehicle. So we've been working, and they've been working with and have software installed at a number of automotive companies and other industrial companies. So they have a fair amount of experience with how to do lightweighting for vehicles. And you can do this really with either plastics or with metals. The way to do it efficiently with metals, I think, is through a casting means. But you can also do, like this Renaissance one was done with a boutique motorcycle builder engine mount. And this one was just printed directly to metal, but that becomes generally a fairly expensive part. Typically it's costing in the order of like $4 to $8 per cubic centimeter of material, fully manufactured. So they have techniques within the software that let you do optimization, meaning that you provide a build envelope where you have the space is constrained. You essentially say, this is a space I have available. You then specify some non-design areas, meaning typically the interaction points or mating points with other components in your assembly. And then you just kind of you then apply loads and you let the problem solve. And then the software will then guide, and you can put constraints on it. So you can see here some constraints you can put on the software for different processes. For additive manufacturing, typically there's very little constraint. But it will typically try to build like in a way that, say, reduces support content. And then you can also do constraints that are designed to allow different types of milling or casting, which also can be used or fairly useful for molding. So here's like a little video. I'm going to walk you through the process of the rear swing arm that we did on the vehicle. So this large gray area you see is the available space. Essentially, I took as much room as I had. I saw how much it could swing and not interfere with other vehicle components. I cut out where the tire was and where I needed to mount, say, the brake and the shock and other components. So those other little features are then modeled as separate bodies, and you save it as a step file. And then once you do that, you can go to the CogniCAD solution and you import that step file, which is an assembly of these bodies. So once you have that imported, it'll kind of load and enter it into the space or design space. You open it up, and now you go through the process of setting up your problem for solution. So you first assign the material. In this case, we designed it for cast aluminum. And then you define the design space, the area that it's going to optimize. And then you now pick these non-designed features, which are essentially like bosses in this case, where I know I need to have the mounts for the hinges or the bearing carrier and shock mounts and brake mounts. And then I actually have a couple options if I want to do pure generative design, is what we're doing here. And I can apply different load cases, and I'll be able to weight those later on. But so for each load case, I'm going to set a boundary condition, meaning a part or parts which are essentially fixed in space, and then I'm going to assign loads to other parts. So I brought in this kind of bearing carrier assembly as a part so I could freeze it as a boundary condition. So in this case, I'm essentially saying that the wheel represents 0 position and everything's going to swing around that. So I've done some, like say, kind of free body analysis to understand which loads I need to put on the other elements. And so I'm applying them here. I actually, in this case, also put in some kind of crossbars where I'm applying the loads, and those are there just to kind of carry the load, but they're not part of the design itself. So as I'm going through that, I'm first doing a load case that represents, I think this one was like if you hit a pothole or an impact on the wheel. And then the next load case will be like for a heavy braking or skid. I could then add potentially other load cases to this. You're able to put in loads in different ways as pressures or accelerations. You're also actually able to do like thermal loading conditions in another module if you want to optimize for heat generation or heat exchangers, which is fairly interesting. And then once you've now loaded or created your load cases, we'll then put this into a solver. I'm going to actually skip ahead a little bit. So I have 2 options on how I solve it. I can either solve it and say, I want you to keep X amount of material, or I want you to solve for a minimum stress, or for a target stress value. And so it can do either way. I can weight my load cases separately or give one more weight than the other. In this case, I'm doing a volume fraction, so I'm just going to decide that I want the part essentially to weigh X. So I'm going to see what the loads will be. when I do that. And I can solve it in different resolution settings. And so as you go higher resolution, it may take more computational resources and time to solve. And I can also set here the constraints of the processes. So I set this as an additive manufacturing constraint, and I can set a minimum feature size, meaning if I'm going to cast it, or I may actually change it to casting, but if the minimum feature size mean that's like the minimum like bar or grade, because I don't want very fine elements in my casting. So I'll tell it that the minimum feature I want within a certain range. And then it'll send it off to compute, and it'll design on the cloud. So we're going to skip ahead. It may take an hour or two, depending on how big the job is. But I'll come back and open this up and show you what the result looks like. And you'll have essentially now an optimized result. I can see it in the context of the design space I initially provided. And then I can see my deformations and or stresses in different axes. And I can go and probe and determine where the high points are. So here we're seeing we have like a fairly high deformation under high loading, but the stresses are relatively low or within the range I might be comfortable with for this material. And then you have the option to, there's a number of topology optimization solvers out there. The one reason we use this one is it allows you to save, the output is actually very clear or easy to use with additive, meaning it doesn't require a lot of it doesn't require a lot of repair or manual redesign like some of the other solvers. It gives you also the option to download this as STL or STEP. So in STEP, I can now import it back into CAD, and I can, I don't know, put machining bosses on it or some other tweaks that I may want to do, like for a casting operation, I may want to actually mold in the risers or something, so I can print those along with it and take it into like a casting simulation. So I think that's how the process goes to give you a feel for it. I don't know if we have a lot of people that get involved directly with design of parts, but that kind of walks you through the tutorial of how it works. Typically what I found, I've done this on about 10 or so different automotive components, and I'm usually able to achieve between 25 to 50% weight reduction on those components versus the conventionally manufactured methods. The challenge with this organic design is actually designing it like from the ground up. So these design tools like topology optimization or other generative design, where it might be more guided than a pure solver, or what allow design engineers to come up with geometries which will enable additional performance or lightweighting. And typically these geometries are the ones which can be additively manufactured fairly easily, but may be difficult with other processes. So in this case, as I mentioned, we chose to print the patterns. The cost of the patterns, I would estimate for like the wheel hub that I showed, I'll actually go through those, is relatively low. It's probably more than traditional wax, but there's no tooling involved. So the total cost is a bit of a, it depends a bit on the size of the part. So you also have the option to optimize plastic parts and take weight reduction or performance improvements there. I haven't spend a lot of time talking about that. But both these platforms that Nexa has are well suited for direct to automotive type applications for plastics. And this can help with either low volume applications or middle volume applications, mass customization, or other topics. So to highlight some of the parts we did on this Arcimoto vehicle, I'll just highlight some of the areas where we saved weight and what we achieved. In this case, we're going from a weldment, the way that they were doing it, using mild steel. So they had a 9 kilogram weldment, and it had 11 pieces there. Some bent tubing, some sheet metal, and then some kind of milled components as well that all get fabricated together. We're able to turn that into a single casting that also saved us about 30% of weight. So I jumped too far ahead. The next one's this hub carrier kind of steering knuckle component. Again, we're going from steel fabrication from, in this case, a 9-piece weldment to a single piece. This one actually, we could cast it or you could print it directly in steel. So I actually have one of both now. I first printed it in steel. That was about an $800 print. Doing this as an investment casting, we're able to get the pattern printed for about $30 to $40. It becomes a little more achievable for certain applications. The cost is highly dependent on the build volume that you're utilizing. So as parts get bigger or smaller, the cost changes quite dramatically. The upper control arms, we also reprinted right and left. So here's another case where we went to a cast aluminum pattern and we had about a 50% weight reduction. And finally, we also redid the brake pedal. This is one that's fairly small, and you could fit probably like 6 to 8 of these on the platform. The cost for the pattern here then drops quite a bit to maybe more like $10 or $12 in that range if you do it in a volume application. So I hope that was interesting. I'll open it up a bit to questions now. I think that's the end of the presentation. I appreciate everyone's time to listen. Now, Kuba, do you want to share anything?
Yeah, thanks, Brent, for a great presentation and sharing all the details. I just wanted to maybe do a little follow-up on that, even though this project was made as a proof of concept for the technology and assess the readiness of the technology, it's still alive, and we're at the moment at the feasibility study to enter this project, the commercial phase. So the goal is to check if those components, like for example the swing arm, can be actually implemented on the vehicles or on the serial production. And so far we don't see any obstacles based on our cost-effective study and feasibility study and everything around that. So probably in the nearest future, you guys can see those nicely looking parts on those two vehicles.
Yeah, thanks for that. I didn't mention so much, but this project was kind of one that was handed to me. We did it about a year ago, right before COVID. And we presented this vehicle at the A360 or Abundance 360 Technology Forum in Beverly Hills was our target. The project we was essentially me in my spare time plus my technician. So we're able to get all this designed and produced using the software and additive manufacturing skills in a fairly quick time. So you can think about doing this with design iterations, how quickly it will let you do development. But this kind of technology also can go to production, and we're seeing that with a lot of our customers. I can't always talk about all the customers we have in the loops, but I guess as we launch production with them, you'll be able to probably see it in our social media feeds.
Okay. It seems like we got a couple of questions coming in. First question, Brent in Cuba, with regards to the presentation, is it suitable for just metals, or are you able to do polymers on the same machine? And can you speak to the differences between the materials, some of the challenges?
So our printers actually do polymers primarily. Metals is actually through an indirect process, meaning that we're making patterns forecasting. For polymers, there's two kinds. There's the photoplastic, which starts off as a liquid and will polymerize in the printer when exposed to the UV light. That's the NXE400 technology. We have a lot of different material options there, many of which are suited for production applications and automotive applications. And Kuba can tell you more about our other technology, which is powder-based and uses thermoplastics.
Yeah, the other line of the printers that we are building at Nexa3D are powder bed fusion devices. Those use powdered polymers, like for example, nylon 12, nylon 11, and even high temp materials like PBT. And we use basically high power lasers to fuse a layer of powders. And our machine, our system, which we are actually in the process of rolling out to the market, it's called QLS350. And we plan to reach a full commercial availability in the end of 2021. And yes, of course, with this technology, we can print parts using the generative design. Actually, the QLS technology is very suitable for those type of designs because other than other type of technologies, SLS doesn't need support structure. So the loose powder, which is embedded into the parts and into the build volume, it's supporting the parts in the build volume. And after cleaning these parts from the loose powder, you have basically the net shape part that you can treat, do post treatment like surface finishing and dyeing, color dyeing, or you can use it as it is in your applications.
Okay, great. Also, with regards to, you mentioned it was a two-man project for the Arcimoto. One of the questions is, how fast are you able to iterate between designs?
Typically, I'm able to do a design iteration, like the design portion is taking roughly half a day to a day. If you want to then produce the part, it could take another day or two if it's in plastic. But for, I think, casting, you probably need to leave a week or two, depending on who you're working with and how agile they are.
Got it, got it. What are some commonly used methods to validate the output of the generative design solver?
That's a good question. As these generative solvers come out, they are often have some limits, meaning they'll do conventional like analysis, like you'd get with any other FEA type solver. but like they won't do multi-physics typically. Like I can do thermal separate from structural analysis, but doing them both at the same time or adding in dynamics becomes a bit problematic, or contact analysis. So the most common way to do this is to optimize it in the solver and then take that geometry out and just import it into another method if you have it, or you can go direct to testing. At some point you might set up design rules that work for your application. My experience in like turbo machinery is we had such a tight level or small, say, safety factors involved typically. Like we wanted like an incredibly high accuracy in the analysis that we would, this is the kind of thing that I would expect in those like highly structural or highly stressed environments that you go through a secondary or more traditional analysis, that you have correlation to your material property data and other test data. But there's no reason you couldn't correlate directly to the data you're getting out of the generative design solver for those types of applications.
Okay. Question regarding, are there industry standards certifications for 3D printing?
That is another very good question. I'm actually on like the ASTM committee for additive manufacturing. I'll say that I think primarily it's driven now by the needs of aerospace. And so there's maybe 20 or 30 standards that have been developed in the last 5 years to set the framework for productionization of direct to metal applications primarily. But we're starting to add in these kind of polymer technologies as well. One of the reasons I am promoting the casting aspect is I think the path is shorter. When you go to castings, that's already has like well received and understood in industry, and it's leveraging some existing supply chain basis. So the patterns that you use for castings are really not that critical to the final result. There's just a few details you need to worry about in comparison to if I were to go straight to another metal. For instance, the QLS machine is using thermoplastics that are powdered. They'll behave a little bit different than the, let's say, molded equivalents of those same materials. In photoplastics, like on the NXC400, we actually have a little harder challenge in that those materials technically don't exist. They're not materials anyone's familiar with. So I can say this is an ABS-like material, but the material's been released like 6 months ago, and there's a limited amount of data. So design engineers, we can tell you the basic, this is heat deflection temperature, the stress strain. But if we're looking for like long-term exposure testing and fatigue type testing, that exists only on, say, the older materials, which may or may not be suitable depending on your application.
Okay. Judging from your PPT, it looks like you had automotive as well as aerospace clients. I saw the chassis components. Are there any other system components other than chassis primarily that you have applications for?
There are actually a lot of components outside of chassis. I focused on those because in this case, because we're really looking for weight reduction and to highlight generative design. Components where additive manufacturing can make a lot of sense are like connectors, particularly unique ones, components on the interior of the vehicle, including like ducts or vents that are kind of stylized.
Yeah, the trim components, okay.
Trim components, exactly. And the systems are out there now, particularly with some of the stuff that like QLS does. You'll print like a powdered part, but there are other companies then you can work with that will dye them to do color matching to the Pantone colors and kind of automated polishing, so you can have fairly consistent results on the fit and finish for the ones that are like visual parts or require touch and feel, and
Okay.
you want to control. And then there's kind of the raw parts that may look a little rougher, and you may see some of the layer lines. Typically we're using like around 100 micron layers, so there might be a little bit of stair stepping on some of these parts.
Okay.
But it's fine enough that it tends to polish off pretty nice. And
also, I think one worth mentioning over here, one discipline that is emerging pretty heavily right now is part consolidation. So at the moment, I think this is the leading vertical in aerospace industry. For example, in rocket engine design, there is a couple of companies out there who are using additive manufacturing, different techniques of additive manufacturing to consolidate the parts of the rocket engines, and they have amazing results. I've read a couple of days ago about the rocket engine, which consisted originally out of almost 500 different pieces, and they were able to reduce it to 28. So this reduced significantly the room for error, and also the tooling necessary to not only manufacture but also assemble this product. So this is another field that we are exploring very heavily in both resin and powder polymers, but also in metals. And it can be done in metal casting as well.
Okay, great. Can you guys speak to the size of the parts, the footprint that you're able to print to for your machines?
yeah, on NXE 400, it's a 16-liter volume. So the build area on the platform is about, say, roughly, let's say 6 by 10 inches, and then about 14 inches tall, or a little bigger than that, I think. So 270, so 11 inches by about 6.5 by 14. Okay. And then on the other printer, it's what, 350 millimeter cube?
Yeah, it's 350 by 350 by 430 millimeters of effective build volume.
Okay, great. We have quite a bit of student contingency within our attendees, so this next question is a three-parter for our student bodies. What advice do you have for SAE student members in regards to this technology being additive manufacturing? The second part, is this being covered with current engineering education, in your opinion? And then lastly, who are the leading schools or universities for 3D printing?
It's a good question.
So,
I think
so maybe
go ahead.
Yeah. So we couple of years ago we started a program with Exponential Works with University of Santa Barbara, where we were able to take on board the interns from this university, mechanical engineers, I think, most of them, and but in my opinion, there is no clear answer to that question yet. There are courses around the world which are targeting additive manufacturing, but there is not many students out there who already finished those courses that we can, the sample is so small that we cannot say how good they are. That's number one. And also number two, the technology advancement is so fast that for a university it's difficult to keep up. So for my advice, would be, to choose programs with very strong mechanical engineering background, material science. Me, myself, I finished Metal Foundry faculty in University of Krakow in Poland. And this gives me a huge background in terms of mechanical engineering and material science in terms of metals. And then by yourself, you need to study hard the technologies and the field that you're interested in, and listen to the market and talk to people like Brent, who is actually hiring heavily in Nexa3D right now, what the requirements would be for the certain positions.
Yeah, and I'd
Anything
add
to add,
that,
Brent?
yeah, if you can hear me okay.
Yeah.
I would add that I've observed that most of the new students coming in tend to have a lot more affinity for the process. A lot of the like the cohort when I came into the industry, there were still drafting tables in the design room, right?
Sure.
So I was there, came in as like the one that knew how to do CAD, and that was the new technology. And what I'm seeing now is most or a lot of engineering schools have introduced some kind of 3D printing, and it's advanced quite a bit. There's so many versions of it that no one really masters all of them typically. But being good with 3D CAD and now these generative design tools are actually not that intuitive if you've spent your time learning CAD tools. The method that you go to design to, like, you're essentially directing a computer to design parts for you rather than specifically or explicitly modeling surfaces and curves. Some of the more experienced engineers that may understand the requirements for that application really well and what problems you'll run into may struggle to use these tools. So I think to be successful, you want kind of a combination of both kind of the young, flexible minds that can pick up on these tools as well as the experience that's out there. I don't know if any one school stands out. I think most are okay. MIT does have a pretty well-known additive manufacturing course for professionals, but most decent universities do have a number of printers available. They may not have explicit courses in additive. I actually think the designing for additive is one of the biggest challenges. So understanding the process and then how to design for it. It's similar to other processes like machining. You can more or less machine anything, but you don't really want to, particularly if you're going to volume, you want to optimize it for that process. The same for molding, and the same is true for additive. If you want to go to high volumes, you have to really understand the process and the material well to have high throughput and high yields.
Okay. Great information. I think with regards to presentation, we'll wrap it there. Where can we find Nexa for our student body members or any information with regards to career activities? Feel free to shout out your website or some contact information.
Yeah, we just had finished a funding round, so I think we have a lot of open positions right now, and you can go to Nexa3D.com, and I'm sure you'll learn about it. Or either of us are, I think, fairly easy to find on LinkedIn as well.
Okay. Any last comments from yourself or Kuba before we wrap it?
I think that was a great piece of information that Brent shared with us. It's edge of the technology, and if you're really into additive manufacturing and would like to know more about that, yeah, hit me up on LinkedIn or Brent as well. We are happy to discuss, answer any questions. Even maybe there are some internship opportunities in our company at the moment. So if you're up for that, let us know and maybe we can work together.
Well, I'd like to thank you, gentlemen, both for your time. The information was great. I think our attendees got quite a great deal of information. So we'd just like to thank you for your time and opportunity to learn about Nexa3D.
All right. Well, thanks for having us. All right.
Okay. And just before we wrap this, I wanted to present some information on the section itself, how to get in contact with SAE SoCal. You can see our web links, www.saesocal.org. Also our social media information on LinkedIn, Facebook, Please subscribe to our YouTube channel. Then last but not least, my name is Delbert Boone. I'm the Meetings and Tours Vice Chair. You can see my email as well. And then also my colleague, Dean Case, who's responsible for membership. His email is membership@sasocal.org. So for those attendees, we appreciate your participation. And as we bring this to a close, monitor our website for future activities, and we appreciate your support. Have a good evening. Thank you.